Alright everyone, and welcome to the AI Research Roundup. I'm your host, Alex. Today, we're diving into a paper from May 6th, 2025, titled LiftFeat, 3D Geometry-Aware Local Feature Matching. This paper introduces a new, lightweight AI model called LiftFeat. Its main goal is to improve local feature matching. That's the process of finding corresponding distinctive points between different images, especially in tough conditions like bad lighting or repetitive patterns. It achieves this by adding 3D geometric information to the 2D visual features. Specifically, it uses what are called surface normals, which essentially tell you the orientation of a surface to enhance the raw 2D descriptors. A descriptor is a numerical fingerprint of a visual feature, helping the AI distinguish it. This is super useful for things like SLAM, or simultaneous localization and mapping, in robotics. Alright, and for those looking to get hands-on, the authors have shared the official implementation of LiftFeat on GitHub. You'll find the code for training and evaluation, plus some demo scripts and pre-trained models to really test out this 3D geometry-aware matching. So it's a great resource if you want to dig deeper into how this works. Okay, so Figure 1 really helps visualize this improvement. It shows feature matching on a tricky low-texture scene. Panel A uses a method called superpoint, relying only on 2D visual information, and you can see some incorrect matches highlighted in red. The little histograms also show the distribution of its descriptor features. Panel B then shows the 3D geometric normal map. That's the map of surface orientations we discussed. Finally, Panel C demonstrates LiftFeat, which uses this 3D information. The result is more accurate matching, with more green lines for correct correspondences, because incorporating 3D information enhances the distinctiveness of those 2D descriptors. So, after seeing the improved matching in Figure 1, Figure 2 here gives us an overview of the LiftFeat architecture itself. It starts with an input image, which goes through a series of convolutional blocks. These are like filters that extract basic visual patterns, and a fusion block. Then, the network has separate, quote, heads to predict the key point map, the initial descriptor map, and importantly, that surface normal map. This normal map is learned using what's called 3D geometric knowledge supervision, essentially using another AI to help generate training data for these surface orientations. Finally, the 3D geometry-aware feature lifting module takes these raw descriptors and normals. It uses multi-layer perceptrons, or MLPs, which are a fundamental type of neural network, to prepare the data, and then self-attention layers, which help the model focus on the most relevant information, to combine them into the final, enhanced descriptors. Okay, so after looking at the LiftFeat architecture in Figure 2, Figure 3 really shows these capabilities in action. It compares LiftFeat's feature matching performance side by side with two other methods, Superpoint and XFeat, across various tough scenarios. The top row tackles lighting variations, the middle one deals with low texture, and the bottom features repetitive patterns. In all these examples, LiftFeat, which is in the rightmost column, consistently shows more green lines. Those are the correct matches, and fewer red lines for incorrect ones than the other methods. This visual evidence underscores its robustness in these challenging conditions. So as we've seen, especially with those examples in Figure 3, LiftFeat really does a great job in tricky situations. The big idea here is that by cleverly adding 3D geometric knowledge, specifically those surface normals, to the 2D feature descriptors, we get much more robust and accurate matching. This kind of improvement is really vital for applications like better 3D reconstruction, or even for robots navigating complex environments. Well, that's our look at LiftFeat. Thanks for joining me, Alex, on the AI Research Roundup.